Hello everybody, welcome to the course VLSI Design Flow RTL to GDS. This is the 26th lecture. In this lecture, we will be continuing with constraint. First, let us look into that what is the expected environment in which our design work, right. So, this is the design, this is the design which we are considering or for which we are writing the SDC file. This is what we are designing at this moment. Now, this design will be receiving signals at its input port from the external sources, and it will also be producing signal which will go to the external circuit, right. Now, when the environment in which the circuit is working, that will put additional constraint. Why? Because we are assuming that the whole system is synchronous, right. There is a clock source, right, there is a clock source which is generating the clock signal, and it is used both in the external world and it is also used in our design, right. So, remember that many a times we partition our design into multiple blocks. So, then this my comp will be actually our block, and the external that we are referring to, it may be the top level design, right, in which our block is being instantiated, right. Now, this external circuit or the top level design might be operating at the same clock generator, it would be using the same clock generator if we are using a synchronous system, right. So, now in this system, the signal that will be coming at the input port in, right, at this point, it will already undergo some delay because of this C1 element, the flip flops and the in, right. And if because of this these delays, the time period that will be available for our internal flip flop to capture the data, that will be reduced, right. That information must be captured, otherwise what will happen, this D1 delay, the implementation tool may make it much larger or allow it to be much larger, and the timing when it is this system, the my comp is put and made combined with overall system, because of the external delays and the part of the clock cycle that is used by the external circuit elements, though because of those delays, the setup and hold violation will happen in our flip flop, right, that is in FF1, right. So, the signal entering the design at the input port encounters delay and we need to model that. Similarly, signals leaving our port leaving the port out, that also will also encounter delay because of our the circuit elements in our design, that is my comp, and also it will undergo delay externally before being captured, right. Now, the signal that we are generating at the output port, that will be captured externally, right. So, and what we want is that wherever it is being captured externally, there also the setup and hold requirement should be met by this flip flop F out, right. So, to meet this requirement, we need to inform the tool that which is doing timing analysis for our tool, that is my comp, we need to do that inform that there is some constraint on the output port. It is not that this delay D2 can be arbitrary, right. So, to model the effect of data being captured externally, we need to add some constraints at the output port, right. Now, what is that constraint? We will just see. So, in this slide what we are showing is that we need to consider, or we need to bother about what is the environment in which our circuit is operating, or our circuit in my comp in this case is operating, because the external environment will also impose constraints within our design, and that needs to be captured while we are doing the static timing analysis of our design, because if we do not do that, then when our design will be plugged in at the top level, there will be a failure. Okay. To avoid that failure, we have to model the external environment and put that in constraint in the SDC file. Now, let us look into how we can put those constraints in the SDC file. So, suppose this is our module, my comp, right. Now, signals which is entering our design, that will get delayed before entering the design, right. So, it will be delayed. So, the lesser part of the clock period is available for the signal to reach the flip flop within the design. So, the some part of the clock period will be taken by this D in and C E1, right. Note that the effect of this C lat is already being taken into account by the source latency, right, that we saw in the previous slide. So, here when we define the clock and specify the clock latency, then the effect of C lat is already taken. So, we need not bother about C lat, but we need to bother about delay of CE1, delay of this flip flop, that between clock to Q pin and D in, because the data that will be generated by this flip flop externally, that must be captured in the flip flop FF1 in the next clock edge, right. So, there is only a clock so there is one clock period which is available for the data to traverse from here to here and meet the required time requirement at the D pin, right. So, this delay that will be encountered by the signal which is coming at the port in, that delay is modeled using the command SDC command set input delay. And how do we model it? So, we model it by adding the delay of C1, the F in of F in the delay in between of the timing arc between clock pin and the Q pin, and the delay of D in, right. So, these three components will be taken, that much will the delay will be there. Suppose this delay was 100 time units. So, first we define the create clock, right. First we define the create clock and the frequency that it is being generated. So, the create clock is defined on the port. So, this port name should be actually clock underscore port, right. So, we define the clock create clock on this clock underscore port, right, and we give the name of the clock signal as CLK, right, and then we write the command set input delay, and then with reference to which clock we are referring to the set input delay, we give the name of the clock get clock CLK and use the option minus clock to define that we are saying that we are defining the clock signal, and then we define the value 100. So, 100 represents the delay of C1 plus clock to Q delay plus D in, and then we say that on which input port we are defining this constraint. So, this constraint is specified on the input port in, and therefore, we have written get underscore ports in, right. Now, at the input side or in the input port, we also need to define the transition of the signal. Why do we want to do specify the transition of the signal? Because if we have a design, right, if we have a design and a signal is coming at this input port, right, to compute the delay of the instances which are directly connected to this input port, we need to know the slew of the signal, right, which is coming at it, right. Because remember from the earlier discussion that the delay of say this inverter depends on two things. The first is the input slew, right, the input slew, that is the slew of this signal, how fast it is transitioning, and the load at this load seen by this inverter, right. So, the load can be computed internally by the tool, right, because this is because it is known that the attributes of the instances and other things are known by the tool which is doing SDC for our, which is doing STA for our design. But the behavior of the external signal that the tool cannot comprehend or cannot derive on its own. Therefore, we need to define that what is the slew at the input port. From the input port, then it will do a kind of slew propagation that we have discussed in the earlier lectures, and the slew will be known inside our circuit by slew propagation. But at the input port, we have to define, right, because the tool cannot derive what is the characteristics of the signal which is coming, right. So, we use the command set input transition to model slew of the incoming signal, right. For example, we say set input transition 10, on the input port in, right, suppose this the name of this port was in. So, we say that the input transition is 10 time units, meaning that slew of this signal is 10 time units for the that needs to be used for the max case or the setup analysis, and it is for the rise. Similarly, we can do for the min case and also for the for the fall transition, right. So, we can define 4 different values if you want, right. Now, sometimes the behavior of that what will be the input transition, that is not known, but what we know is that what will be the driver that will be driving the input port, right. In that case, we can use the command set driving cell, right. So, suppose we give the command set driving cell, and we say that the cell that is used to drive our input port is buff1x, and the library name is tech 14 nanometer. We can, so the set driving cell command is attached to this object that is port in. So, what it means is that we will have our design, right. In our design, there will be an input port like in, right, and then on this input port in, there is a driver whose name is buff1x, and it is contained in the library tech 14 nm, and that is driving it, right. Now, while we have discussing the delay calculation, we saw that the tool computes delay by creating stages. So, in this case, a stage will be created based on the wire that we have inside our circuit, the driven pins, that is I1 of the pins of the I1 and I2, right, and a driver which is what is specified in the set driving cell, right. Now, the input waveform at the at x, that the tool can use some default value or an ideal case, and using that and the load that is seen by this wire W and the load seen at the input port and the capacitance of the wire W and the input loads of I1 and I2, like the pin loads of I1 and I2, the tool will compute the waveform at this input port by making this a stage and creating this stage and doing the delay calculation. And that this note that this waveform that we obtain at the input port, that is y in this case, that is we give an input as x, right, and we got the behavior at the or the waveform at the input port in as y. Now, this y can be non-linear also. The limitation of set input transition command is that it assumes a linear behavior, right. For only for a linear signal we can define a slew, right, but for a non-linear signal we cannot define a slew, right, and the signal that may come to our design, that may be non-linear also, and in that case set driving cell is a better option to use rather than set input transition, because in that case non-linear behavior of buff1x can be automatically computed by the delay calculator by using advanced delay models such as ECCS or ECSM. Now, let us look at the output side. Now, at the output side, the signal leaving a design must meet the setup and hold requirement of the flip flop that captures that signal, right. So, the constraints of the external flip flop is modeled using the command set output delay. So, let us understand how we can define the command set output delay to model the setup and hold requirement of the external flip flop, right. So, suppose this is our design, right. This is our design in which we have my comp, right. So, my comp is our design and it is producing a signal at the output port out, right. Now, in this output port, so the signal generated at the output port is undergoes delay of D out, and then it is captured by this flip flop F out, right. Now, the setup and hold requirement of F out must be met, right. So, that the setup and hold requirement of F out must be met, because the entire system consisting of our my comp and the external element is a synchronous design, right, or is a synchronous system. So, we need to meet the setup and hold requirement of F out, right. Now, if we do not model it, what can happen is that the delay D2 will be unconstrained, and therefore a major part of the clock cycle may be consumed by D2, and when it reaches D out and then D pin and the D pin of this F out, then the required time may not be met, right. The required time at F out may not be met, and therefore we have to somehow model the setup and hold requirement of F out at the output port, right. But the problem is that we at the SDC file is or whenever the tool is doing STA, the tool is only seeing this part of our circuit. This is only our circuit is the tool is seeing when it is doing an STA. It has no information of the external environment, that what type of flip flop it is that will capture our data produced at out, what will be the setup time, what will be its hold time, what will be the delay D out, right, and so on. So that the external behavior is totally unknown to the STA tool when it is doing STA of MyCom. So we must model those effects somehow in the SDC file, so that the effect is captured while doing STA of our design MyCom. So what the tool will do in that case is that it will do the timing analysis at the output port out by considering an ideal flip flop which is sitting close to the output port and having a delay of OD which is specified by the command set output delay, right. So what we need to do is that while providing the set output delay command, we need to choose the value of the set output delay set output delay or this element OD such that the timing requirement of this circuit and this circuit both are equivalent, right. So note that when the tool is doing STA of this circuit, it is assuming that there is a virtual flip flop connected in adjacent to the output port, right. What is a virtual flip flop or what is its characteristics? The characteristics is that its setup time is 0, its hold time is 0, right. So that the simplest thing that the tool can assume is that the setup time is 0, hold time is 0. So whatever the effect needs to be modeled for this flip flop, that has to be contained in this the value that we specify for set output delay, right. So the delay of OD, this element needs to be chosen such that the setup hold requirement in the actual circuit, this is the actual circuit, and the equivalent circuit, this is the equivalent model that the tool will use for doing the timing analysis for the output port out, these two should be exactly same, right. So the delay of OD is specified in the set output delay command. So let us look into this an example and understand that how we can choose the or determine the value of OD, right. Let us assume that this is our circuit, and there is an external circuit which is having a delay of say 400 picosecond on this of D out, and the setup time of this flip flop was 30 time units and the delay on the clock path was say 20 time units, right. Now the same circuit will be analyzed using set output delay command, right. Now the set output delay command has got a value of delay which will be there in the set output delay command, and that delay we have to find out. We have to find the delay of OD such that the timing analysis of the original circuit and the model that will be considered by the STA tool, those match exactly. So let us first understand that what will be the timing requirement in the first circuit, the original circuit, right. So we consider the setup analysis, the late setup analysis or late analysis, the early or hold analysis we can do this in the similar manner, right. So in this case, if we consider the flip flop F out, right, F out, then what is the arrival time of the signal at this deep in, right. So suppose the clock was generated or the signal was generated at time 0, then it will undergo a delay in this path, right. We let us call the delay between this clock and this output port as T int, internal delay, right, and then it will undergo a delay of 400 picosecond, right. This is the arrival time of the signal at D, right. Now, for the setup analysis, the arrival time should be less than the required time. What is the required time? So, if the clock time period is TCLK, then the next clock edge will be generated at TCLK, then it will undergo a delay of 20 picosecond, and then the clock edge should or the data should be stable at least 30 picosecond before the clock edge. That is why we have to use minus 30 in the required time, right. So, this is the constraint that we have for the actual circuit, right, and for the circuit that will be used by the STA tool in the analysis, what will be the arrival and required time? So, the arrival time will be same, right, from in the internal part, and then it will have a delay of whatever the set output delay command specifies. Let us call it at TOD, right. So, the arrival time at this point will be T int, which is delay, that is the signal undergoes internal to our module MICOM, right, and TOD is the time that is specified in the set output delay command, right. And then what is the required time? Required time, the next clock edge will be generated in TCLK time, right, and we are assuming the virtual clock has setup time of 0, there is no circuit element on the clock path, and therefore, there is no delay here, and the setup time is 0, and therefore, the required time is same as TCLK, right. Now, what we are saying is that we have to find the value of TOD such that this constraint and this constraint are exactly same, right. Now, how do we find it? Now, T int are same in both cases, right. Now, let us take TCLK is on the RHS, right. So, we take this 20 and minus 30 on the LHS. So, this constraint becomes 400 minus 20 plus 30, if we take it on the other side, and it becomes 410 is less than TCLK. And what we have constraint on this side, we have TOD is less than TCLK. So, what it means? TOD should be equal to 410 picosecond, right. So, TOD is 410 picosecond, and we will write the constraint set output delay as follows. So, first we will be writing the name of the clock, right. So, say we write the command create clock name as sys clock and minus period 2000 picosecond, and then the port name clock in this case, right. So, clock here, and then we write set output delay, and then we give the value 410 that we derived here, and then we say that max. So, max will be used for the setup analysis, and then we give the clock which is being referred to in this which is basically generating this clock, sorry, this signal at the output port out. So, the name of the clock is sys clock, right, that the name that we have given here, and then we write get underscore ports out where we want to apply this set output delay command. So, this is how we specify set output delay for the case when for the setup analysis. Similarly, we can do for the hold analysis, and in that case we will give the option minus min, right. And this we can also define separately for rise and fall and so on, right. So, these things you can look into, or the more options that are available for the command set output delay, create clock, create generated clock, and other commands that we are discussing. You can look into the manual of this tool, that manual of the tool that you will be using for STA or logic optimization or design implementation. Now, at the output port, we also need the information of the load, right. So, suppose this is the design that we are making, right. Now, in this design, if we consider an inverter which is driving an output port out, right. Now, to compute the delay of this inverter, we must know that what load it is driving externally. For example, there may be a wire which is connected to the output port before this is being driven by the another, or that before it is connected to an inverter which is reading the signal out, right. So, there will be a capacitance associated this wire and the input pins. So, to do a realistic delay analysis of the instances which are directly connected to the output port, we need to specify this external load, and to specify this external load we use the command set underscore load. So, we can use it, for example, set underscore load, this 0.039 is basically specifying the external load, external capacitive load in terms of library unit. It may be picofarad or femtofarad or whatever the library, what is the unit of capacitance in the library. And then we say that on which port we are applying this constraint out in this case, right. So, we are applying at this port out. Right. Now, let us look at a few constraints which defines the functionality of the, or which are related to the functionality of our design. Okay. So, there are some situations in which we do not want the STA tool to do an analysis that is a traditional STA analysis. So, traditional STA analysis is that we are checking for the setup time requirement at the next clock edge and the hold timing requirement at the same clock edge, right. That is the conventional timing analysis or for a synchronous circuit. But in some cases, we want that the tool should not do that kind of analysis. For example, we know that there is a flip flop and there is another flip flop, and between these two flip flops there is a path which is connected, connection is there, but the behavior of the function or the behavior of our circuit is such that the signal that is generated from this Q pin will never be reaching this D pin, because of the functional Boolean function or some relationship that exists between the logic elements in the path from Q to D pin, right, and therefore, that signal cannot propagate in this path. Now, if that is the case, then we can specify a command set false path between these two flip flops, and can mention also the name of the instances through which this, or the name of the pins through which this path go through the map. So, we can specify that command, or we can write set false command, set false path command in our SDC file to specify that do not do timing analysis for this particular path, because the signal is not expected to traverse or propagate synchronously or on this path, right. So, we are making an exception, right. So, if we know that there is a path which where signal cannot propagate, then we can use this command set false path. It will relax the timing for that path and may help in improving the PPA of our design, or it will also help in suppressing false timing violations, right. So, if we know that the signal will not propagate from one point to another, then if we do not use this set false path command, then we may get lots of violations which are actually not needed, right. So, if we can use the set false path command to suppress those violations. And then there are some cases where we want that the signal or we allow a signal to go from one flip flop to the next flip flop or next sequentially adjacent flip flop in say more than one clock cycle. For example, suppose there was a flip flop, right, and it was producing data and it was traversing through the combinational circuit element and then reaching another sequentially adjacent flip flop. But we know from our functionality that this Q pin will change only every say 4 clock cycles, right. It will be held constant for say 4 clock cycle, and then only it will change a value, right. So, if we know that kind of functional behavior, then we can allow the tool or we can inform the implementation tool and STA tool that for this particular path do not do conventional STA analysis, but make an exception, allow say 4 clock cycles of delay in this path, right. If we do that, then probably this the combinational logic between these two flip flops will be not highly optimized for timing, and therefore, the area savings can be done or PPF of the circuit can be improved. So, this is basically relaxing the timing constraints and therefore, some QR benefit can be expected, right. So, let us see that how this set multi-cycle path command is used to specify that for given path we allow more than one clock cycle for a data to propagate. So, if we do not use set multi-cycle path, then the behavior of the tool is something like this, right, which is shown here. So, the setup analysis will happen in the next clock edge and the hold analysis will happen in the same clock edge. So, the allowed window in which the signal can propagate is from this window, right, the window that is highlighted in this figure, right. Now, if we say that set multi-cycle path 4 with a setup time with the option of manage setup from this FF1 CP, right, this is FF1. So, this is FF1 CP pin, right, and to FF2, this is D pin, right, to FF2D, we say that for the setup analysis we allow 4 cycles to for the data to traverse in this path, right. So, if we give this command, then what the tool will do? It will shift the window of checking as shown in this figure, right. It will check for the setup analysis at the 4th clock edge, not at the same the first clock edge, but at the 4th clock edge. But what will happen to the hold analysis? It will be checked just one cycle before that, similar to the behavior of the synchronous circuit. It will be checked at 3rd clock cycle. So, what it means is that if the data if the data starts from this Q pin and reaches D pin, say in this in the 2nd clock cycle, then there will be a hold violation, right, because the data is coming before the hold check edge, right. But ideally what we want is that, or typically what we want in our design is that we want to relax the timing constraint. We want that the data can traverse any time between the 0 clock edge and the 4th clock edge. We want to expand the window of checking, right. So, if we want that behavior, and most of the time we want this kind of behavior, then what we want this kind of behavior, right, that the setup check happens at the 4th clock edge, but hold clock edge. So, hold checking should happen at the 0th clock edge only, right. So, in that case we have to write 2 commands. The first is related to manage setup, where we give the multiplier as factor as 4 as earlier, but we also need to add a command which has an option manage hold, and where we have the path multiplier as 1 less than what we have specified in the setup, right. So, here we have specified as 4 and then we specify 3 for the hold check. Then what it means is that move the hold check 3 clock cycles to the left side and it will come at this edge, which we want, right. So, if we want our window to expand for the checking, then we should use both the setup option and hold option for the set multi-cycle path command as shown. Now, sometimes we need to apply constant value to the port or pin, right. So, in the earlier discussion we had seen that we do what is known as MMC, multi-mode multi-corner analysis, to account for variations that will happen in our circuit, right. Now, we said that for multi-mode we have different SDC files, and in SDC files we say that some some value of or some signal will take assume some constant value. For example, we may say that there is an SDC file which is for a design say scan.sdc. In that case, in scan.sdc file, the scan enabled signal is taking a value of say 1, right, and there may be other changes also involved in the scan.sdc file. Maybe the clock frequency will be different than what there is in the functional mode and so on. So, this scan SDC file will be a separate SDC file, right, and in that if we say that in the scan mode, if there is some signal, for example, scan enable is assuming some constant value, for example, the input port scan enable is always having a value of 1, right. So, to specify that, we can write in scan SDC file the command set case analysis value is 1 and the name of the signal where we want to apply that constraint. Similarly, there can be a mode in our circuit which is known as sleep mode, and we can write a sleep.sdc for that particular mode, right. And in that case, suppose there is a signal or a port whose name is sleep mode, that signal might need to be kept at constant value 1 during the sleep mode, right. So, we can specify it using the command set case analysis. So, if we want that some signal, maybe a port or a pin in our design is held to a constant value for certain mode in our SDC file, then we specify it using the set case analysis command. Okay. So, if you want to go deeper into the topics that we have discussed in this lecture, you can refer to these references. So, now let me summarize what we have done in this lecture. So, in this lecture we have looked into the constraints and the SDC file and how we can apply various types of constraints such as clock constraint, the constraints related to input and output delay, and also the constraints related to input output ports such as load and transition, and also specify some functional constraints such as false path and multi-cycle path, right. Now, with this we complete one important part of our of this course, that is timing analysis and timing constraints, right. And in earlier lectures we had looked into the RTL synthesis and logic optimization, and at the end of logic optimization we said that we got a net list in terms of generic logic gates. Now, from next lecture onward, we will look into that how these generic logic gates are mapped to standard cells and how the timing and power and other considerations are taken into account in the in the design implementation or the logic implementation, right. So, we will be looking into technology mapping in the next lecture. Thank you very much.